Also in section 9.5, we have what's called the comparison test. And here's an example of where the comparison test will be convenient. So let's look at this expression here, k squared minus k over k to the third plus 4. And if we sort of look at the end behavior of this function, we know that it's going to be similar. It's going to behave in the same way to k squared over k cubed or to 1 over k. So our comparison series is going to be just that, the series 1 over k from 1 to infinity. And so what we want to look at is, how does this end behavior look of this comparison series? Does it converge? Does it diverge? And whatever this series does, then the comparison series should do the same. So remember that this is a special series, and a lot of times that's what's going to happen, is that your comparison series is going to be something that is easily determined in terms of its convergence or divergence. And so if it's one of those special series, we can often find out quickly whether it does converge or diverge. And the harmonic series, we know, diverges, and the comparison series then will also converge. I'm sorry, I meant to say diverge. Whatever the comparison series does, the original series will do the same. So my original series here also diverges. So the comparison test is only handy if you can find something that compares, again, that's easily determined whether it converges or if it diverges. So there's a good example there. Let's finish up by just going over some guidelines for choosing a test. So at this point we have special series, a few different ones. We have a couple of different tests. And so if we are asked just in general without any guidance, does something converge or does it diverge? Here are some things that we can do in terms of flow of making that decision. So we can often start with the divergence test. Pros and cons of the divergence test. Pros are that it can be used on any series. You don't have to meet any criteria to use it. Cons are that sometimes it can be inconclusive. So we can only determine that something diverges with this test. We can't conclude that it converges. So we can start there, and if it's inconclusive, then we keep going. Next, what we might do is look for one of our special series. And so special series, we have the harmonic series, which also led into the P series. We had geometric, which was easily handled, and we also had our telescoping series. So you'll want to look for those possibilities and use their own special rules there. If it doesn't fit any of those, you might try the integral test. Okay? And what I'm going to say about that is that you're going to try the integral test if it's reasonable. And remember, with the integral test, there are several conditions that you have to meet before you can use it. You have to make sure that the series that you're working with is based on a function that is positive, decreasing, and continuous. And so it has to meet that criteria, and also it has to be something that's easily, integrated, basically. And if it is positive, decreasing, and continuous, then you should be able to find its antiderivative easily. So that's the downside of the integral test. The upside is that you'll always get a conclusion. You'll know, is it divergent or convergent? And then finally, if none of those works, then you might go with your root ratio comparison test. The thing about these three tests is that they're very limited in terms of when they're convenient. So it's often not convenient to compare the ratio of two terms in a series. It's definitely not convenient in a lot of cases to take the kth root. And then also in terms of comparison, you might not have a quick and easy function to compare it to. So these only work well and efficiently in specific cases. So you sort of want to wait until the end to figure out if one of these might work.